Good morning.
Good morning.
Can you hear me?
はい。
I cannot hear you.
Hello?
ちょっと待ってね。One moment. I changed my computer, so. Dafira-san, could you talk?
Hello?
Okay. I can hear.
Okay. Happy New Year, Sensei.
Happy New Year. Well, I cannot say happy. This year we had a
Very,
disaster and the plane crash and yeah. Okay.
very rough starting.
Starting. One moment. Okay. I cannot open my camera. So just one moment. Camera device. Okay. Anyway.
Right.
So, Zabura-san, you start first.
Okay. Can you see my screen, Sensei?
Yeah.
Okay. So I start to study about Harris model to apply for our study. So this one, in Harris model, they have two type of model, like two different length of beam. So they categorize one is C 3.5 and C 4.0. So I compare the Stera TD analysis and Harris, so we can use the model accurately. So this basically a pushover based on the
Zafira-san, what is a C 3.5 and C 4.0?
It's a type of a structure model, a name of the structure model. So the difference is the length of the beam. So state 3.5, the beam is 3 meter, and the 4.0 is 1.2 meter.
Okay.
Okay. So, and then we combine viscoelastic and friction damper. So for example, we take 40% viscoelastic damper, which is around 200 kilonewton, and the friction damper here is about 170 kilonewton. So viscoelastic is a little bit bigger than the friction damper. So we want to see if the Stera model can limit the force at 170 kilonewton. So and then we have to calculate when we combine the viscoelastic and friction damper, we have to calculate the input inside the Stera TD. So basically in Stera TD we have C, K1, K2, and the F. So the F is maximum at 170, and then we calculate this is the damping, and this is for the stiffness of viscoelastic, and this is for the friction damper combined with the viscoelastic. I use this from this book, Sensei, to calculate the KB. And after that, I put inside Stera TD as this one. And after that, I check the performance of the Stera TD. So this is for longer beam, which is 3 meter. We can see there's a bit effect damage, little bit damage on the wall. This is only viscoelastic, and this is viscoelastic. So this one, the input for 200 kilonewton viscoelastic damper design. So we can see that it can exceed more than 200 kilonewton. But if we use viscoplastic, so we limit the force at 170 kilonewton. So we can limit here, and we can see the wall is a bit better. But if we compare to shorter beam, we can see the performance of the whole building is actually better, and the force in the performance of temper also become better. And I also check for the from every aspect. So this one is compare Centro and Kobe. For this one is if you can see, the blue line is for steel beam and the gray line is for the viscoelastic only, and for the orange color is for viscoelastic with friction damper. So if we see 3-meter beam, the longer beam, so as we already said, the maximum force is 170. We can see the orange line is less than 170. And the ductility is written in this box. So it's actually less than 0.5. And if we compare shorter beam, actually it's performed better. So basically if you can see, this is your force in the damper. So it's actually less than 100 kilonewton. Here is like almost 170, a bit bigger. But if you use a shorter beam for the coupling beam, actually it's performed better. So it's less than 100 kilonewton, and the ductility also perform good. And then we can see at the wall, the shear wall, and the performance of viscoelastic plus friction is better. And if you use shorter beam, is perform better than. So if you can see here, the shear at the wall is less than 20,000 kilonewton, but this one is slightly over 20,000 kilonewton. And then this is the ductility. So this is for the longer beam. We can see the ductility varies a bit larger compared to the shorter beam. So we can see the ductility is less for El Centro is less than 1.0, and here for wall 2 less than 1.5.
One moment.
Cannot follow.
Yeah.
Okay. Okay, I can show you this one, the drift and acceleration. There's a big difference, for example, especially for the accelerations. So if we use longer coupling beam, we can see the performance of the viscoelastic and viscoelastic with friction is greater than the blue line. So blue line is the steel beam. But if we use 1.2 meter, we can see that the story drift and acceleration is actually less than the steel beam. So in my conclusion is, if you use a proper length of the steel coupling beam, or the length for the damper to replace put the damper, actually the performance of the building also affected.
Why, if you,
Mm.
I mean, could you show me story drift of short beam?
Short beam here.
This is short beam,
Yes.
and story drift is 4 centimeter. El Centro. Okay.
This is this is short beam, Sensei, 0.4. This is longer beam, so it's 4 centimeter. It's about 10% longer. This is for short beam. So the maximum is 0.6
Okay.
centimeter.
Only steel beam. The story drift of short beam is 0.2.
0.2.
0.2 centimeter.
Steel beam, it doesn't move a lot because it doesn't move because it's very stiff steel beam. But for damper, we allow the steel beam to move, so it have more displacement compared to the steel beam.
So if the beam is short, two coupling wall like moving together.
Yes.
Right. So
yes.
How about the coupling beam ratio?
Coupling beam ratio.
What is the difference? Long beam and short beam. How much coupling wall ratio?
I believe the short beam have higher degree of coupling compared to the the longer one, because longer beam you create larger moment at the coupling beam.
So if the beam is long, two wall somehow move independently, right?
Yes, yes,
And the short beam, two wall move like together.
yes. So
So
it's
you can say, how to say, so if you put the damper in the coupling beam, so the effectiveness depend on the coupling beam ratio, a coupling wall ratio, maybe.
yes, degree of coupling. Yes,
Degree of coupling.
yes.
Do you think you can change degree of coupling? I mean, in this case, only you try two cases. One is long
Yes.
beam and another one is short beam.
Mm.
Yeah. So, and the result is completely different.
Mm.
So if you change the length of beam, you can change coupling wall ratio.
Yes.
I think it's better to control the parameter, not by the length of beam, by the coupling ratio.
Okay. I think we can do that, because even for length, story height, for example, 6 or 12 or 18, the degree of coupling also changes. So we also can look into that.
So, can I share my screen?
はい。
そっか、できないかな。One moment, I will try. Yesterday, I have a trouble with my computer.
It's okay.
I will see. Sorry. ダメか。ダメかな。ダメか。OK。
I can see your screen, Sensei.
Yeah, I know. But I supposed to, I mean, draw the graph by my finger. I mean, but this screen doesn't recognize my.
How about paint?
Yeah, I can draw by using my mouse. One moment. 違うな。Okay, let's see. Can you see?
Yes, Sensei.
So, let's see. So horizontal axis will be coupling ratio. Brush. Coupling. I forgot. Coupling wall ratio.
DOC, Sensei, degree of coupling. DOC.
Degree of coupling. Okay. Degree of coupling. Yeah. And vertical axis, maybe reduction ratio. Reduction ratio, I don't know. So it is a response of, let's see, no damper, divide response with damper. This is with damper. And this is no damper.
Okay.
So probably it should be less than 1.
Okay.
Yeah. So, and if coupling ratio, degree of coupling is small, I mean reduction ratio I don't know. May not be so. So ejection ratio. So if it go in this way,
Mm.
you can say optimum degree of coupling is this value.
Mhm.
I don't know if you can draw this kind of graph, but anyway, you have 1 degree of coupling for short beam
Yes.
and 1 degree of coupling for large. Which one is larger degree of coupling?
The short beam.
Short beam is here.
Yes.
Long beam is here.
Mm.
Okay. And the vertical axis, please think about how to show, effectiveness of damper.
Okay.
For a ratio of response reduction or energy dissipation of damper,
Mm.
or well, any, I don't know, please think about what is a good
Indication.
indication. Yeah. Yeah, it's better to normalize by the energy dissipation or no damper, something like this.
Okay.
Okay. So, what else do you can show me today?
That's all for today. And I did the spider for
Yeah,
Python.
Python program.
Last time, I already, let me show you. So I studied the basic Python from my friend. So this is for only plastic. So you want me to combine plastic and visco to combine?
Yeah. Ahmed-san made a program for viscoelastic only.
This is for the viscoelastic. So this is the graph. And then this is for viscoplastic. So I write this graph already including viscoelastic and the friction damper, right? Sensei?
This is only bilinear.
Bilinear. So you want the graph should be like this and more circular when we combine both damper. Is that what you mean, Sensei?
Yeah.
Okay.
I don't know. Ahmed-san, did you try?
Yes, Sensei. I try to create only the friction damper without elastic device.
So you mean?
I can show you, Sensei, in my presentation.
Okay.
Can you hear me, Sensei?
Yeah.
First, I created hysteresis for the first code for the viscoelastic device.
Yeah. Okay.
Which is this one, and this is the graph for many amplitudes. Also, I created the code for the viscoplastic, and it was like this.
So in elastic range, it must be same as viscoelastic in elastic range.
Yes.
But it's just a straight line. Why?
But it's a straight line because I didn't combine it yet.
You didn't combine it yet.
Yes.
Okay.
So the code for
So
the
you
plastic. Yeah.
so you will combine. I mean, you will combine the programs.
Yes. I try to combine them.
Do you know how to do? Well,
Actually, I've tried, but I failed to do that. But I'll try again.
hmm. Okay. I will show my computer. あ、そっか、ダメだ。I don't have a, editor. ちょっと待ってよ。Oh, okay. Anyway, please try to combine. And if you have a problem, maybe we can discuss.
That's it.
Okay. So, okay. Anything else, Ahmed-san?
Yes, for me, after just I prepared these two codes, I also prepared just a summary for dissertation and some papers sent for me by Zafira-san. It's related to Harris. So Harris shows how to estimate the dimensions of the coupling beams, many types of coupling beams, but I focus on the steel coupling beams. To determine the required area of the web based on the plastic design from this relationship. Then to determine the required section modulus using the material resistance factor and the moment on the steel beam. And we have to check the dimension of the web and the flange of the beam and to control the out of plane buckling to make sure that the plane is safe for related to the out of plane buckling and to ensure that the coupling beam remain elastic along the embedment length. We should verify this the web thickness during the embedment length inside the cable shear wall.
What is the embedment?
Embedment is the length of the where the beam penetrate the
okay.
RC wall. Yeah.
This is a circle. You mean you marked the circle in the picture?
Yes, Sensei.
In that area. Okay.
He also recommended to provide the additional intermediate stiffeners in the embedment portion in the coupling beam. Also for the embedment length, to calculate the required embedment length of the steel beam inside the RC wall, he proposed this formula based on the shear capacity of the embedment and the material resistance factor, also the eccentricity factor, which depends on the shear and the distance from the applied shear to the center of the wall, as we can see in this graph, E equal length plus the effective length plus C, which is the cover, over 2. Then after that, after getting the required embedment length and after estimating the size of the steel coupling beam, we also can calculate the degree of coupling if our coupling beam system in a building. You can estimate the interaction or the connection between our coupling beam system and the structure system. He proposed two formulas. I just presented here one of them. This is the formula number one to calculate the degree of coupling, which depends on the area of the walls and the Young modulus of the coupling beam and the RC wall. It depends also on the story height of the building, the moment of inertia of the building, and the of the beam, the clear span of the coupling beam. Which is, if it's long, the degree of coupling will be different. If it's short, the degree of coupling will be higher. The lever arm between wall centroids and the number of coupling beam for each story. After that, he proposed something that during the analysis, we should reduce the effective stiffness of the coupling beam by 0.6 kEI, which K represent the reduction in flexural stiffness due to shear deformation in the beam. Actually, but I have one question related to this part. I don't know if we should apply this to the nonlinear analysis or not, because I know that the nonlinear analysis also consider the degradation in the strength during the analysis. So I don't know if we should apply this for the nonlinear analysis or not. Last thing is related to if we want to calculate the coupling beam angle of rotation, we can calculate it from the angle of rotation of the wall itself using this relationship, which depends on the theta b, which is the rotation angle of the wall, and the length of the wall also depends on the length, the clear length of the coupling beam. So that's all, Sensei.
うーん So in this Harris paper, he assumed the beam will yield by flexure, or beam is elastic.
Yes, Sensei.
But they assume plastic hinges at the end of the beam.
Yeah, at the end of the beam, also at the base of the wall. Yeah.
Mm. Mm. So the formula of degree of coupling in this slide, it's very little bit complicated.
Yes. There is another simple one. He proposed another simple formula, but here I just presented one of them.
Do you think you can derive this formula?
I can derive, maybe I can try this.
Well, how to say? I don't like using formula, from someone else. Without knowing the reason. There might be mistake in the formula, plus, minus, I don't know, mistake of printing. But if you believe this formula, you don't notice the mistake, right? So if you want to use this formula, you should derive this formula by yourself.
Yes.
Otherwise, you, how to say, you cannot recognize any mistake in the formula. And if you success to derive this formula, you will think about
the results and
another formula or some simplification. But anyway, And I think this is very important paper. Hmm. Hmm. Okay. So Zafira-san, Ahmed-san, maybe we should discuss in my room.
Okay, Sensei.
Yeah.
Actually, Sensei, I know there's one paper that compare with this from Ahmad some formula that he showed and the simple one that in the book. There's one book discussing about the degree of coupling. Actually, there's one paper comparing with this formula. So if we want to really specify the material of the building, we can use this formula, the long formula. But if we only have simplified model, which one is very easy to be calculated, we can use the simple formula, which is more easy. So there's one paper I can share with him later that compare between these two formula. So yeah.
So I think degree of coupling in this formula,
Yes.
probably the beam is elastic stage. The
Okay.
formula, basically the wall and the beam, both element or all element behave like elastically, and they calculate degree of coupling.
Okay.
But if you consider inelastic behavior of the coupling beam, or if you put the damper in the coupling beam, degree of coupling may change depending on how much nonlinearity.
Okay.
Because if beam got the damage, the beam will be getting very, stiffness is getting very small after damage, right? So degree of coupling definitely change.
Okay.
So that's why he proposed to put a modification factor for the stiffness of the beam. Okay.
Modification factor.
Let's say. Yes, this one.
No, it's not non-linearity. It is shear stiffness, shear deformation.
Okay.
This is elastic shear deformation.
Okay, Sensei.
So, and maybe you can think about the equivalent stiffness of the damper, and you can put the equivalent stiffness of the beam, coupling beam, inside the formula. So, なんていうのかな、Yeah. We must think about the definition of degree of coupling. I mean, and the degree of coupling may change depending on nonlinearity of the coupling beam. So first, if beam is elastic, two all like moving together, but after coupling beam start to yield or damper start to work, two will probably behave independently. So coupling ratio, degree of coupling may change depending on the nonlinearity of the coupling beam. Anyway, we must discuss maybe face to face.
Okay.
Let's decide the date of the meeting.
Okay, Sensei.
And Zafira-san, you should write a paper this year. At least you are second year of the
second year, first
second
semester.
year, right? So before summer, I want to ask you to publish one paper, and another paper maybe
After summer.
after summer.
Okay.
And yeah, so so anyway, we already have a two Stella 3D building model and damper. So we need some strategy how to なんていうのかな、formulate logic of the paper. What is the purpose of the paper and what is the parameter we should change and what is the conclusion we can obtain.
Okay.
Yeah. And we must think about something new, original idea.
Right.
And also we must also think about the experiment we will do with the Sumitomo Rikko company.
Okay.
Well, actually, they worry about the friction damper. I mean, if you put the friction damper in the middle of coupling beam, you know, viscoelastic damper can deform any direction, right?
Yes.
Tension, compression, shear, any direction. But a friction damper only can deform one direction. There is a long hole with bolt, and the bolt is sliding.
Yes.
So the なんていうのかな、and if you put the viscoelastic damper in the middle of coupling beam, the beam can deform, I don't know, not only vertically, maybe also tension, shear, also bending. So it's not so easy to combine friction damper and the viscoelastic damper. We need some idea how to put it together.
Okay.
Yeah, I remember you draw some picture.
But you want it to move in two directions instead of one direction for the friction damper?
Yeah, just I don't know. I have no idea right now. Okay, but
I would think about it. Okay.
Okay. So let's discuss the date of the meeting. One moment. Today is 5. How about Monday next week?
Monday? Okay.
It's a national holiday in Japan, but actually, I am free.
This is for face-to-face sensei?
Face to face.
Okay.
And Ahmed-san and Zafira-san and me.
Okay.
Three.
Okay, Sensei. Okay.
What time, sensei?
Let's see. We start meeting from 11 o'clock.
Okay.
And we go for lunch together.
Okay.
I will take you somewhere.
Okay.
And after coming back, maybe we can continue to discuss.
Okay.
So 11 o'clock.
Okay, sensei.
Okay, Sensei. Thank you.
Yeah. Zafira and Ahmed. 11 o'clock. Okay. Okay, who is next? Ataya-san?
Yes, Sensei. Since I don't have anything to show, but as you sent me yesterday the link of the building engineering website.
Yeah.
I saw the website and I didn't find anything about the template. For example, the font size, the font. and everything which is needed to prepare the format.
So it means any format is okay, probably.
Maybe not, because as I downloaded some paper from their website, all the paper has the same format, but it's very difficult to understand from the PDF which size and which font is used in that papers.
Maybe if we send the text and the figures, they will arrange. They're the publisher. I mean, companies, they arrange all materials. So what you need to submit is word text and the figures and tables.
Okay, Sensei. I will send that up to 9 of this month for comments.
9 of this month?
Yes, Sensei. Next Tuesday.
Next Tuesday?
Yes, Sensei.
So you prepare the manuscript?
Yes, Sensei.
Okay. So please show me before you send.
Okay, I will send you, Sensei, before.
Yeah.
Yes.
And I will be corresponding author. So it means I will submit the manuscript.
Yes, Sensei, I will send it to you.
Okay.
Yes, Sensei.
Oh, so you already have all materials.
Yes, Sensei, I prepared actually a little.
Good. Very good. Okay. Okay. 真島くんなんかある？今日は。相談すること。
いや、特にないです。
実験の、試験体の方は、今日も作業してるわけ？
今やってるところです。
今やってるところか。
はい。やりながら聞いてて。
ご苦労様。今日はちょっとね、今日はちょっと忙しいので、昼飯は連れていけないんだけど、
はい。
じゃあ、よろしくお願いします。Okay, so, beside of the meeting with Zafra-san and Ahmed-san, maybe we will decide, I mean, next meeting, date of the next meeting. Let's see. So, Monday next week, we have a discussion, and after that, I'm a little bit busy. 10:30, 40. How about 15? 1 o'clock. No, 1 o'clock monitoring group. ダメだな。10:30, 1 o'clock. Wow. 困ったな。大学で教科書見学。建設学対話。結構忙しいな。10時半、7時。How about 3 o'clock, 15?
I'm okay, Sensei.
Okay, so control group meeting. 3 o'clock, 15. I hope I have a paper of Harris paper. あるかな？
I can share with you.
Do you save all document in Google Drive?
Not everything, Sensei, but I will transfer for you, and then I will give you the link.
Yeah. Please put the important document, papers in the Google Drive.
Right.
And please give me the link.
Okay, Sensei.
Yeah. Okay. Shall we finish?
Right.
Okay. See you.
Sensei,
Yeah.
Sensei, sorry. When is the deadline for submitting the master thesis, Sensei?
Ah, okay. マスターセースです。One moment. あたやさん、you know this website, 教務システム。this one. Do you know? Have you visited here?
Yes, Sensei. Yes.
And there's a
Yes, Sensei.
FAQ here.
Okay, Sensei.
And if you go down, number 7, degree application.
Okay, Sensei.
And in this list, let's see. Maybe this one. Yeah. The number 1, procedure. Let me see. No, no, not this one. Okay. Submission of thesis. 違うかな。No, not this one. これかな。違うか、違うな。これは違うよね。これは3月か。completion schedule. これはインターナショナルプログラムか。書いてないね。書いてないね。
Sensei,
Yeah.
I think I remember last time they emailed to the student about the submission.
This is a lab meeting memo, maybe. Record of lab meeting.
I think the office will send to the student about the submission.
Well, it is written here. 2nd of February. This is a thesis.
Okay, thank you, Sensei.
And the abstract 1 week later. And the presentation is 19. Okay?
Thank you, Sensei. Yes.
Yeah. And your presentation already decided here. No, it's a preliminary defense. Already finished.
Yes, Sensei.
Okay. But it is written here, submission.
Thank you, Sensei. Yes.
Okay. Shall we finish? Okay, see you.
Thank you, Sensei.